Welcome back everyone. So this is lecture 9 and today we're going to talk about Bayesian methods. That's the plan for today. So today we're going to cover two different approaches in Bayesian methods, a parametric approach and a non-parametric approach. And as an example of parametric approach, we're going to look at Bayesian linear regression, and as an example of a Bayesian non-parametric approach, we're going to look at Gaussian processes. Right? And before we jump into today's topics, a quick recap of what we covered in lecture 8. So lecture 8 was all about kernels, right? And we saw that a kernel, a function k of two parameters x and z, and these are typically two examples in your training set or in your test set, etc. These are examples. A function of two of our examples, k, is called a kernel if k of xz can be represented as phi of x transpose phi of z for some phi that maps your examples to a p-dimensional real space. Now p here can be infinite, so p could be infinity, and some of the properties of the kernels, we saw that first it needs to be symmetric in its arguments. So x and z, the arguments can be swapped and it needs to evaluate to the same value. And for all, for any finite collection of examples, and these examples could be any examples, not necessarily a training set, for any finite collection of examples, the kernel matrix that you construct such that kij equals, the value of the ijth cell in the matrix evaluated as the kernel function evaluated on the ith and jth example is positive semi-definite, right? And basically the Mercer's theorem tells us that this property 2 is a necessary and sufficient condition for k to be a kernel. So if you have a function k that satisfies this, then it necessarily must be a kernel, which means it can be represented in this way. So this was the definition of a kernel, and these are properties, and Mercer's theorem says, we can go back and forth. This set of properties is equivalent to the definition of a kernel. And in an informal way of thinking about Mercer's theorem is a matrix which is possibly infinite by infinite dimension is PSD if and only if every submatrix is PSD, right? And why is and the way to think of why a kernel k represented like this, is PSD is this statement is basically telling that k, which this is possibly infinite dimensional. If k can be represented as phi transpose phi of two examples, then you have this kind of an eigen decomposition or some kind of a symmetric decomposition, that you can take the matrix k, the infinite dimension matrix k, and split it into some phi, where phi is a collection of columns, where each column is the function phi I of x. For example, if you have phi of x equals x square, x cube, log x, some set of features, then we would call phi 1 of x to be x square, phi 2 of x to be x cube, and so on. So each of these phi I corresponds to one such function, right? That's the general idea you want to have in terms of thinking about kernel matrices, that these the corresponding features of the feature map that is implicit to the kernel are like the eigenbasis of that PSD matrix. Right? Now today we're going to and the other thing we covered in the last class was SVMs is a kind of classification algorithm which tends to work well with kernel based methods, right? The reason I say it tends to work well with kernel based methods is because we saw that kernel based methods can be applied to linear regression, it can be applied to logistic regression, where the number of parameters that we save with the kernel method is generally equal to the number of examples that we have, whereas with a more classical linear regression or logistic regression, the number of parameters we save is equal to the number of features, right? So we move from saving parameters, which used to be an order of the number of features that we have with classical linear or logistic regression, to kernel methods where we save coefficients, one per example, which means in general you would expect kernel methods to not work very well when your data set grows a lot. SVM was a special case where the coefficients of the examples tend to be sparse, meaning most of the coefficients will be 0, and that makes SVM very attractive as a kernel method, because not only do you get scalability to infinite number of features using the feature maps, but you also get scalability with number of examples because your coefficients will be sparse. Okay. Any questions about that before we move on to today's topics? Okay, cool. So let's jump in. Bayesian methods. So far the methods that we've seen can be loosely called frequentist methods. And that's because we assumed that an unknown parameter theta, which we assumed to be some unknown constant, right? We assumed that theta is some unknown constant, vector valued but unknown constant, right? And the way we go about estimating theta was to define a likelihood on theta. So we would define a likelihood L of theta to be log p of, say, your data parameterized by theta, right? And we would consider the negative of L of theta to be our loss function, and then we would estimate theta equals arg min of negative L of theta, and this is the same as arg max theta L of theta, right? So this is the maximum likelihood estimate of our parameters, and in order to do this, we implicitly assume that theta is some unknown constant, right? Now today we are going to look at a different approach to attack this problem, where theta is a random variable. We think of it as a random variable that is unobserved, right? So this small little change, which may seem innocent, is basically the fundamental difference between Bayesian methods and frequentist methods. In frequentist methods, there is some unknown constant theta, whereas in Bayesian methods there is a random variable theta which is unobserved. Now the moment we think of theta as a random variable, there needs to be some kind of a probability distribution associated with it, right? Just calling something random variable is necessarily incomplete, because we want to say what is the associated distribution with it, right? And when the first thing we do in Bayesian methods is to assign some prior probability distribution on theta. So we believe that theta comes from some prior distribution, right? And then we observe our x, data. We believe that the data comes from the distribution from p of x given theta. This is generally has the same mathematical form as the likelihood function, but it is different philosophically in the sense that we are implicitly believing theta as having some kind of a prior distribution. But the functional form of P of x given theta and the functional form of P of x, semicolon theta parameterized by theta are exactly the same, right? But the interpretation is different. And now the main difference between the two is with the classical methods, we perform maximum likelihood on theta, on the log likelihood to get an estimate of theta, right? But in the Bayesian method, what we do is we apply the Bayes rule. So in Bayesian methods, we come up with P of x given theta, and this is P of theta given x is P of x given theta times P of theta over P of x, right? And P of x, we don't know what P of x is, but P of x is integral P of x given theta times P of theta d theta. So basically it's the numerator, take the numerator and integrate out theta, and that gives you P of x, right? Is this obvious why this equals this, right? If it's not obvious, just the numerator is P of x comma theta p theta, right? P of x comma theta is P of x given theta times p theta, that's P of x comma theta, and then you marginalize out theta from it, right? So this is Bayesian method. This is the Bayesian approach, right? So in the Bayesian approach, there is no loss function, right? We don't take maximum likelihood estimates. We don't calculate gradients. We don't do gradient ascent or descent. There are no, closed form MLE estimates. All we do is apply Bayes rule and update our beliefs about theta given x, given the data, right? All that we do in Bayesian methods is apply Bayes rule, which is why it's called the Bayesian method. Okay? And with this, this is essentially the counterpart of performing maximum likelihood estimate. Here we calculate the posterior distribution. So this is called the posterior distribution. Right? And in case of machine learning, the way we go about using Bayesian methods is as follows. So in machine learning, especially in supervised learning, we are trying to learn a mapping between x and y's, right? So the data in a machine learning setting will also have y's over here. So x and y is our data, and the likelihood. So maybe let me. So in supervised machine learning, we start with theta having some prior distribution, right? And then we observe x and y, and over here y comes from P of y given x comma theta, right? Here we make no assumptions about the distribution of x. X's are just given to us somehow. We only assume y given x follows theta, whose prior is we make some assumption. So x is always given, right? We don't say anything about x's, right? And from this we calculate the posterior distribution P of theta given xy, and this will be P of y given x comma theta times P of theta divided by P of x comma y comma theta given x. And there is we also make the assumption that theta is independent of x, and this becomes just P of P of y given x. There is something P of. So P of theta given x comma y is P of y given x times P of x over this should this correct. So yeah, this is right. P of y given x. Now so we calculate the posterior. The posterior is on theta, and from the posterior distribution we construct what is called the posterior predictive distribution. Right? And the posterior predictive distribution is basically P of y star, where x, y, x star. So x star is a test example for which we only observe the x, the input, and x and y are part of your training set for which we have observed both the inputs and the outputs, right? And this is called the posterior predictive distribution, and this is basically integral of P of y given x comma theta times P of theta given x comma y d theta. Right? So this is the general recipe of using Bayesian methods in machine learning. Right? So this is the Bayesian methods. If you're only interested in theta and you're not interested in making predictions, this is more classical Bayesian statistics, where you come up with a posterior distribution on your theta and you're all done, right? Whereas in machine learning, we want to use it to make predictions on unseen examples. We are given x and y, and we want to make prediction on x star of what y star is. Yes, question?
For the posterior, should it be P of, on the right hand side, in the numerator, P of theta given x?
Yeah, so the question is, should this be P of theta given x? Yes. P of theta given, it should be P of theta given x, but because we make theta and x as being independent, this will just be just P of theta. Yeah, good question. We make the assumption that x's, on which we are conditioning to observe y's, those x's are independent of theta. It's a pretty common assumption because, yeah. A good question, right? And the way you think about this equation, which looks pretty complex. It's an integral over the product of two probabilities, and then you're integrating out theta. But this actually has a very this is y star and x star, and this is x and y, the training. So these are the tests, and these are the training. But this has a very nice interpretation. So the interpretation is something like this. With the posterior distribution, we are coming up with a probability estimate of how likely a given theta is the correct theta. Right? So P of x theta is a probability distribution over theta. Right? And theta is essentially our model. Right? Now, what's happening here? If you just look at this expression, think of theta to be some fixed, some fixed vector. Right? P of y given x theta is like making a prediction for y for some given value of theta. Right? And what we are essentially doing is considering the set of all models. So let's say this is model 1, model 2, model 3, and model 1 corresponds to some theta 1, theta 2, theta 3. But theta 1, theta 2, theta 3 is a full vector. So if so maybe let's call it theta 1 superscript 1 to indicate that it's a full vector, theta 2, theta 3, right? So what we are essentially doing is we are taking the prediction of y given x for every possible value of theta. So each of these will make a prediction of y, right? And then we are calculating a weighted average of all these predictions where the weights are decided by the posterior distribution. Right? So the posterior distribution is giving you some kind of a distribution over your models. Right? Theta is the model. Right? Once you know theta, you can make a prediction. For example, in case of logistic regression, if you know theta, we do x transpose theta, get a scalar, run it through the sigmoid function, and that's our that's our p of y. That gives you the probability of whether y is 0 or 1. What's happening here is the interpretation here is we are considering every possible value of theta. Right? There are infinitely many possible values your theta vector can take. Right? And your posterior distribution is giving you a probability distribution over all these values of theta. What's the probability that a given value of theta is the right value? Right? That's what the posterior distribution is telling you. And for prediction, we are essentially taking the prediction from every possible, infinitely many possible values of theta and aggregating them by a weighted average where the weights are decided by the posterior distribution. Yes, question?
There is a true underlying distribution that is for this data. And let's say one of these three models is the closest to that actual distribution.
One of these models?
Yeah. So why are we going to take contributions from the other model when one of them is actually going to represent the other one most closely?
So the question is, if one of them is closest to the true model, then why are we taking the prediction from all the models? And the answer there is that we are not sure, right? The posterior distribution tells us that it is likely coming from this model. It may also be coming from this model, but my belief that it's coming from this model is 21%, and my belief that it comes from this model is 20.1%. It's giving you a posterior distribution over the parameters, which basically is like our belief of what the true value of theta is.
So is this going to be highly susceptible to our choice of prior when we start?
Exactly. So the choice of our prior is going to determine what our posterior distribution is going to be, right? And in a way, Bayesian methods are subjective because it takes this subjective element of the person who is modeling, right? If the person who is modeling believes that theta comes from a prior distribution where it is Gaussian, then you get some posterior distribution, and therefore you make some kind of prediction. Whereas, if all else being the same, you just believe that your theta comes from, say, a Laplace distribution, then your prediction would be something different, right? And this is probably the biggest criticism against Bayesian methods, that there's a lot of subjectivism in play here, that the subjectivism comes into picture based on what prior you're choosing for theta.
In the prior, you cannot choose any value of theta to be 0, right? Any probability can be.
Yeah, so the question is, can your prior assign 0 probability to any models? So if your prior distribution over theta assigns 0 probability to some value of theta, then necessarily in the posterior also it will be 0. So in general, it's a bad idea to choose a prior which will assign 0 probability to some, right? So you want to think of this as, so this the predictive distribution as the expected value of p of y star given x star comma theta, where theta is sampled from p of theta given x y, right? So this is the training set. From the training set, you construct a posterior distribution, right? And then you take the prediction of p of y given x, where theta here is a random variable that is distributed according to the posterior distribution. And this expectation is equal to this. Yes, question?
Why is this model any more subjective than, say, something like a generative model, where you also have to decide y given x is, say, Gaussian or so on?
Yeah, so I guess the question is, how is this different from generative models that we saw before?
Or why is this any more subjective than something like that?
Yeah, the question is, why is this more subjective? It is more subjective because we are making yet another assumption of the way theta is distributed. For example, in GDA, when we studied GDA, the mu and sigma, we did not have a prior on them, right? They were just some unknown constant that we estimated using maximum likelihood. Whereas if you took a Bayesian approach there, the mu's and sigmas of your GDA would also have prior distributions on them, and you would calculate a posterior without doing maximum likelihood. Okay? Yeah. So so this is one way to think of the posterior predictive distribution, that you're essentially taking the prediction from every possible model configuration that you can come up with, and then taking an average of those predictions as a weighted average, where the weights come from the posterior distribution. Right? And this approach is essentially what one might call parametric. We call it parametric because P of y given x comma theta is, has some functional form for which theta is a parameter, right? So y given x theta is generally, for example, it could be, just take 1 over 1 plus e to the minus theta transpose x. And because of this functional form, the degree of freedom that we have is to just change theta, right? And that in a way limits the set of all possible models that we can consider. The set of all possible predictive functions that we have is limited by this functional form, right? And different values of theta gives us different specific predictive functions, but the set of all these predictive functions is still somewhat limited. And one way to kind of see that limitation is, supposing we have right? Let's say we have a regression problem, right? Now, what's the correct hypothesis form for this? Maybe it's linear, or maybe it is quadratic, right? Or maybe it is cubic, right? Or maybe as you observe more data, maybe it is a much higher order polynomial, because there probably is some well predictable varying variance in it, right? And by limiting ourselves to certain family of parametric functions, we are essentially saying no matter how much data is given to us, we just cannot be flexible to fit all this variance, even though that probably is not noise and is true signal, right? That's the fundamental limitation of parametric models, is that the functional form of the hypothesis function limits us from being flexible even in the presence of a lot of data which suggests that there is some other pattern. Which is why there is interest in non-parametric methods. Right? The non-parametric methods, on the other hand, are the way to think of non-parametric methods is that we consider the set of all possible functions, right? And that seems pretty expansive, right? We're considering the set of all possible functions, and it's hard to even imagine and write it down on a piece of paper, what that class even looks like, right? The set of all possible functions, and then we let data kind of decide which function from that set we actually want, right? So in non-parametric methods, we generally think of some function f and assume no functional form whatsoever, right? We just work with a function f, which could be any kind of function. Right? So before we get into the details, let's have a look at Bayesian linear regression to get a better feel for how the Bayesian method works in case of regression, and then we'll move on to non-parametric methods, that is Gaussian processes. So Bayesian linear regression. Bayesian linear regression. So again, in Bayesian linear regression, we start with a training set xi, yi, I equals 1 to n. This is a full training set. Right? It comes from some unknown distribution, and we make the assumption that yi equals theta transpose xi plus some unknown noise epsilon, where epsilon I comes from some normal distribution sigma square, and theta comes from some normal distribution tau square. Right? So this looks very similar to the standard linear regression setting that we had, except we also apply a prior on theta. Right? This is the only extra line from standard linear regression. And now good question. So what is tau square I? So in this case, each epsilon I was a scalar. So sigma square was a scalar. Over here, theta is in Rd, and x is also in Rd. So theta, this was a standard, this is just a normal distribution, but this is the multivariate Gaussian distribution, where 0 over here is a 0 vector, and tau square I is a covariance matrix, which is in this case a diagonal covariance matrix where the diagonal values are tau square. Right? Thanks for asking that. Right? So we are given this, and in case of the standard or the frequentist approach to linear regression, we constructed a likelihood function for. So in the frequentist approach, L theta equals log of p of y given x theta, right? And this turned out to be, if you remember, log 1 over square root 2 by sigma square exponent of y minus theta transpose x square minus half over sigma square, right? And essentially in this it boils down to just the square term. Everything else just cancels out or becomes a constant factor, and we end up getting the square loss function, right? And we perform so performing maximum likelihood was like minimizing least squares. So that was the frequentist setting. But what about the Bayesian setting? In the Bayesian setting, we get P of, we don't do maximum likelihood. So, in Bayesian linear regression, we just construct P of theta given S. So let's call this S. S is the full training set. Right? We construct P of theta given S using Bayes' rule. And in case of linear regression, you can work it out. This will be theta given S will be distributed according to a normal distribution, mean 1 over sigma square A inverse x transpose y, comma A inverse, where A is given by 1 over sigma square x transpose x plus 1 over tau square I. Right. So you can work it out. The theta given x is distributed according to, so the correct way to write this would be theta given s is distributed according to a normal distribution, a multivariate Gaussian, with this being a mean vector and this being the covariance vector, where A has this form. This question?
Just a question about the first line I want to talk about. The posterior, if in our prior we are assuming theta is independent of x,
yeah.
Even in the posterior, is P of theta given x comma y just P of theta given y? So
So is the question, is P of theta given x comma y equal to P of theta given y? In general, no, because independence may or may not change once you condition on extra variables, right? Yeah, in general this is not true. Yeah. Was there a question? Yes. So this is an arrow over y which says it's a vector.
Why is the output labeled y matrix?
Yes, this is from the training set. This is this y. Right? And this looks a little cryptic. Maybe we can simplify this a little further. So, right, if I bring in A over here, so this is going to be x transpose x plus, because it has an inverse, x transpose x plus A is 1 over sigma square. Okay, that goes out. Square over right. What do we have here? So here we have a normal distribution where the mean over here has this form and some variance, and you might recognize that this looks very similar to the normal equations, right? In the normal equations we had x transpose x inverse x transpose y. Right? This looks very similar to the normal equation, except there is an extra diagonal matrix that is being added to x transpose x. Right? And I think somebody asked the question when we were deriving the normal equation, how did we invert x transpose x? What if it's not invertible? Right? And one answer is over here. In Bayesian methods, assuming prior on our theta to have some tau square and some noise epsilon square, we get this extra diagonal matrix that is added to x transpose x. And you might remember, if you take a positive definite matrix or any matrix in general, and if you add a diagonal matrix, then you are essentially increasing the eigenvalues of that matrix by the corresponding diagonal terms. Right? Which means now even if there were some eigenvalues that were 0, by adding this diagonal matrix, you're essentially making all of them non-zero, and that makes it invertible. Right? So this is also called regularization. We're probably going to see this in the context of regularization as well. Adding this term is effectively equivalent to regularizing our model, right? And well, maybe this is a giveaway, but this this observation is probably going to solve a big chunk of one of your homework problems in your next homework, but that's fine. So the theta given S in the Bayesian setting is now a distribution that is centered around this value, which is very close to the maximum likelihood estimate, and has some variance over here. And so this was the posterior. And next we construct the posterior predictive distribution. The kind of mental map you need to have is calculating the posterior is like fitting a model, even though we are not doing gradient ascent. Calculating the posterior is like somewhat similar to estimating your maximum likelihood estimates, and calculating your posterior predictive distribution is like calculating the function which will make predictions on your new data. And in case of the frequentist method, there wasn't a distinction between the two, but in Bayesian methods there is a distinction. Yes. A justification for this. So this has quite a lot of algebra that I don't want to go into. You can just just believe me that if you work out the algebra, you're going to get this form.
Work out what algebra?
The apply Bayes rule to calculate the posterior. Yes, question. So if so the question is in the posterior predictive distribution. Yeah. So this is y star. Right. So in the posterior predictive distribution, the setting is that you're given the training set x and y, right? And on new examples, you only know x. You need to make a prediction on them, right? You don't know what it is, right? And for that, we estimated by this probability distribution with the. Yeah. So this will give us a probability distribution over y star, and if you want a point estimate, it is quite common to take the expectation of this distribution as the if you want to make a point prediction for y. A lot of times we want just point estimates to make a prediction, and in those cases it's normal to take this distribution and then take yet another expectation on it as our y hat, as a point estimate of the predictive y distribution. And in many other cases, you actually want to hold on to the full predictive distribution to know what is the uncertainty you have in making that prediction, right? If you have the full predictive distribution for y star, and if that prediction has low variance, if it's kind of concentrated, then it generally means your model is pretty confident of what the value is. Whereas if it's if it has a high variance, then it means your model is less confident. Which brings to a good point. So one of the fundamental points about Bayesian approaches is that Bayesian approaches are used for estimating uncertainties, right? In maximum likelihood estimation, we got a point estimate for theta hat, the parameters, but there was no uncertainty estimation that came along with it, right? Generally, if you have a lot of data, you should expect your estimate theta hat to be, to have more confidence in that estimate. Similarly, if your data was small, you should expect less confidence in your estimate of theta. And frequentist methods don't give you that confidence estimation. Whereas with Bayesian approaches, we are estimating theta given S. And what you will see is that if you have a lot of data, the posterior distribution will be more peaked on certain values of theta. Right? And if you have less data, then your posterior distribution will be more spread out. And similarly, from while making predictions on y star, on x star, if you have if your posterior distribution is pretty confident, is pretty peaked, and if x star is in the region where your training set more or less was where you got it from, then your predictions will also be pretty confident. So P of y given x will also be pretty concentrated. Whereas if your point is far away from where your training set was, then naturally with the posterior prediction distribution will also have a high variance. That's one of the benefits of Bayesian approaches, because you get uncertainty estimates for free, because you're estimating the full distribution of parameters and predictions. Yes, question?
Can you not look at the likelihood function frequentist approach for the same purpose of confidence?
So the likelihood function appears in the Bayesian method. So P of theta given S, theta given S is P of S given theta times P of theta over P of S. So this is your likelihood function.
So like in your frequentist approach, you can still look at the confidence intervals, right? Like you can look at the likelihood function. If that is peaked, you can say that you are sure about your predictions.
Yeah, so in frequentist approaches, sure. So you can get confidence intervals on theta, but the theory is much more well developed for Bayesian approaches. Especially, the theory is more well developed for Bayesian approaches for getting uncertainty estimates. And the way you interpret a confidence interval is also pretty different from the variance over here. So the confidence interval, what you get from a frequentist approach, tells you if you were to repeat this experiment, supposing you have a 95% confidence interval, right? That confidence interval tells you if you repeat this experiment, an infinite number of times, then 95% of those experiments will give you a theta hat in this interval. It is not telling you that your estimate of theta hat lies in that interval with 95% probability, right? Whereas with this, you're getting that, it tells you, what probability the true theta, what is the probability of the true theta lying in some interval given by this, right? So that's the difference between confidence intervals and this. Yes, question?
If we want to decrease the variance of a theta, is that we need to differentiate that term of variance? Is that true?
What's the question again?
We have the distribution over here.
Distribution over theta?
A inverse is the variance of our theta given S distribution.
Yeah.
So, am I right saying that we need to differentiate, like find the minimum of A inverse to get the minimum variance of theta?
So the question is, should we differentiate and optimize this A to get low variance? So here there is no optimization going on. There is no loss function, there is no gradient descent, there is no optimization going on anywhere. All we are doing is conditioning. We condition on this and use the Bayes rule to construct a distribution, and what we get is what we get. Right? It's very different from the frequentist approach. The frequentist approach, we are minimizing some kind of a loss or maximizing some kind of a likelihood to get estimates of your theta. Over here, we just apply Bayes rule and we get what we get.
But isn't what we wish that variance should be low? Isn't it what
We wish that variance is low, and the way the variance will be low is if you have a good amount of data, right? If you have a lot of data, then this will naturally be low. Right? All right. So moving on. So the posterior predictive distribution is essentially y star given x star, comma s, follows a normal distribution of 1 over sigma square x transpose A inverse x transpose y sigma x star transpose A inverse x star plus sigma square. Right? Again, this looks a little cryptic, but it's we can still kind of break it down and make sense of it. What's happening here is we had a distribution for theta, which was some normal distribution. Now, if you have a distribution theta, which is normal, with some mean mu and covariance sigma, where mu here is this and sigma is this, then x transpose theta, this is just a property of Gaussians, is also normal with mean mu transpose x and variance x transpose sigma x. And this is just a property of Gaussians. Right? And now we have our theta to have some normal distribution, and to make a prediction here x star, take x star and we dot product, we take a dot product with theta, because that's what linear regression does, and that gives us this expression, where this expression is just like x transpose mu, where mu is this, dot this with x star and you get this, and the covariance is this. Basically take A inverse and calculate the quadratic form with x star, just like this, and then we add this extra sigma square, because this is the posterior predictive distribution of y star, because y star, the y value that you might observe will have the same noise embedded in it in the test example as well. So to account for what the possible y star you might observe for the test example, you want to account for the extra variance, and you're adding that variance because of and you add the variance because of the IID assumption. Right? So yeah, so this might look pretty complex, but it follows pretty directly from theta transpose x, theta given s, and again, even this, which looks cryptic, is actually very similar to the estimate that we get from the normal equation with some regularization term that comes in. Yes, question.
You might have already explained this, but how do you go from theta given s to y given x comma s?
Yeah, so theta is what we have, so right, and s is x. Yeah, so this is we have the extra s. So if theta has this distribution, then y star is equal to this. Theta transpose x will have this distribution. Right. So y star given x star and s is basically the posterior transformed in this way. Good question. Is this clear? Right? Yeah. So this is just an example of how you would apply a Bayesian method for linear regression, and this is called Bayesian linear regression. Right? It has a few more terms and identities compared to the standard normal equations from the frequentist method, but you get uncertainty estimates by doing this extra calculation. Right? Any questions before we move on to Gaussian processes? Yes, question?
So when we said y star is equal to x star transpose theta, should we add like an exponent term for the noise?
Sure. Yeah. So this would be the mean, and y star equals y hat plus epsilon star. Right? Yeah, good point. Yeah, so this extra epsilon accounts for this extra plus sigma square. Thank you. So in general, Bayesian methods tend to be heavy utilizers of probability theory, because all what you're doing is taking probability distributions and conditioning them to apply Bayes' rule, and that's about it. That's all what you do in Bayesian methods. You assign everything a prior probability, and then you observe some, and depending on what you observe, you condition those probabilities based on what you observe, and you update the beliefs of the unknown. And here the unknown could be your model parameters, it could be the unknown labels of new test examples, but you follow the same recipe. You assign a prior probability to everything, you observe something, and based on the observation, you update your prior probabilities to a posterior probability by conditioning. And you're using the Bayes rule to do that. Yes?
So for the posterior predictions, the mean,
Yeah.
how is that mu transpose X? So mu is 1 over sigma squared A inverse X transpose Y.
Uh-huh.
So the transpose of that would be 1 over sigma squared Y transpose.
Yeah, but here X itself is transposed. So mu transpose X is X transpose Y. Here X is transposed. X star is transposed rather.
But shouldn't the Y come ahead when you're taking the transpose?
So the question is, how is this X star's transpose of this? Right? So add an X theta star transpose and leave it as it is. And this is a scalar, just move it out and you get that.
Oh, mu transpose X is the same as X transpose mu.
Yeah, the dot product is always.
Okay.
All right, Gaussian processes. Before we jump into Gaussian processes, it's probably a good time to again remind ourselves of some of the basics of functional analysis that we saw earlier on, right? In functional analysis, we saw this relation between vectors and functions, right? Now, mentally, it is the same relation between vectors and functions that exists between multivariate Gaussians and Gaussian processes. Right? So multivariate Gaussians are defined on vectors, and Gaussian processes are defined on functions. And it is the same, it's in fact exactly the same relations of how vectors and functions are related, that multivariate Gaussians are related to Gaussian processes. Right? And to start off Gaussian processes, let's review some properties of the multivariate Gaussian distribution. So, properties of multivariate Gaussians. And also, for you to kind of expect what's to come, the functions over which we are going to define Gaussian processes is going to be our hypothesis function. Right? So the idea to have in mind is that the way we went from vectors to functions, we can make the same leap from multivariate Gaussians to Gaussian processes as probability distributions over functions, and the functions over which we want to define Gaussian processes are our hypothesis functions with which we want to make predictions. Right? So, first property of Gaussians is normalization. That is integral with respect to x, p of x mu sigma is equal to 1, where we are integrating over the full vector space. So if you integrate out everything, you get you get 1. And this is just a fact of probability. And supposing we have a vector x equals xa xb, right, which has a mean, let's say this is according to a normal distribution, vector mu a mu b, and covariance sigma a sigma ab sigma b a sigma bb, where you call this mu and this sigma. With this, we have the second property of marginalization. Right? So for marginalization, given given a probability distribution that way, so P of xa equal to integrate out xb from P of x mu sigma d xb. So you take the full probability distribution and you integrate out only a few components, integrate out just xb, and you get P of xa, and P of xa will be normal with mean mu a and covariance sigma aa. Right. More generally, if you have a vector x equal to x1, x2, xd, and if this distributed according to a normal distribution with mu1, mu2, mu d, and covariance sigma 1 until sigma 1d, sigma d1, sigma dd, right? And if you want to estimate the marginal by integrating out, say, x2, let's say we want to marginalize out only x2. The nice property about Gaussians is that by performing this over x2, the normal distribution that you end up getting, the distribution that you end up getting will also be normal with just the corresponding entries related to mu taken out. Right? That's a very nice property of Gaussians. So if you marginalize out x2, then you get a mean. The marginalized distribution will have a mean vector with just that component removed, and the covariance will have that corresponding row and column removed. Right? That's a very nice property about multivariate Gaussians. Marginalizing is super easy. Right? Just take off the things that you want to marginalize, and you get the right answer. Third thing is conditioning. So in the same setting, if you have xa and x as having two parts, xa and xb. In this example, a and b are not necessarily scalars; they are just sub-vectors, vectors with they can have multiple components. So P of our xa given xb given xb is a normal distribution with mean mu a plus sigma ab sigma bb inverse times xb minus mu b. This is a scary looking expression, but let's analyze it soon. Minus sigma AB sigma BB inverse sigma BA. Right? Wow, this looks pretty scary, but it's actually not as complex as you might it might appear at first. Now, to kind of understand this a little more, let's look at a case where xa and xb are scalars, right? So if you have, suppose we have, let's say, a normal vector a, b as normal with mu a, mu b, and covariance sigma a square rho sigma a sigma b rho sigma a sigma b and sigma b square. Right? Any covariance matrix can be represented as this. So take the diagonals, take the square roots, and you can write the covariance terms as the correlation coefficient times the standard deviations of the two. Right? So that's just this is the definition of covariance. Right? So let's see what conditioning looks like in case of this. Right? So a given b is now, according to this formula, a normal distribution with mean mu a plus sigma ab. Sigma ab is just rho sigma a sigma b times sigma bb inverse, so that is divided by sigma b square, times xb. Xb is b minus mu b is just mu b, right, comma sigma aa, that's just sigma a square, minus sigma ab, that's rho sigma a sigma b, times sigma bb inverse, that's divided by sigma b square, times sigma ba, that's again rho sigma a sigma b. Right? We can simplify this further. So this is the same as normal mu a plus, we can cancel 1 sigma b here, so you get rho or sigma a times rho of b minus mu b over sigma b, comma sigma a square times, so 1 sigma b, second sigma b, right, and this is minus rho square sigma a square, right, and this I'm going to just write it as sigma square times 1 minus rho. Right? So now it's much simpler. So what this is basically saying is, if we have a Gaussian distribution over two variables and we observe one of them, b, to have some specific value, then what's happening here? If you take b divided by its mean and subtract its mean and divide by its standard deviation, this is like the z value of b, right? So this is the z value of b. Take the z value of b and multiply it by the correlation coefficient, and then retransform it back into a. Right? Multiply it by sigma a and add mu a. Right? Take b, get it down to this the z value, transform it using the correlation coefficient and then rescale it back into A's range. Right? And what's happening here? Take A, by observing B, the variance of A reduces by a factor of 1 minus rho square, where rho is how much A and B are correlated. Yes, question?
What exactly is the definition of rho?
So rho is the correlation coefficient.
How is it defined exactly?
So the correlation coefficient is so basically covariance equals rho times the standard deviation of A times standard deviation of B. This is also called the Pearson correlation coefficient. It's the same thing. Just the correlation coefficient. How well are they correlated? So if you have a Gaussian variable that looks like this, then you have a positive correlation, because the higher the value of one variable, the more likely the second one is also higher. If it is like this, then it has a negative correlation. If it's a perfect sphere, then there is zero correlation. Right? It's telling you how much information of A lies in B. By observing B, how much can you learn about A? Right? So yeah, this is basically what conditioning is doing. And this is you can think of this as the multivariate version of this. Right? So this is just calculating like the z value of the B vector and then rescaling it back into the A's scale. And over here, from the variance of A, you're subtracting away some variance. Basically, you're gaining information by observing B, right? And this is the same as this, but this is just a multivariate version of this, right? And if you've done some advanced linear algebra, this term, what you see here, is also called the Schur complement. But if you don't know what that is, it's not necessary. But if you know, this is basically the Schur complement of A. All right, and then we have one more property, which is the sum of two independent Gaussian variables. So if you have x distributed as mu1 sigma 1, y as mu2 sigma 2, then x plus y is distributed as a normal mu1 plus mu2 and sigma 1 plus sigma 2. Right? And this is fourth property summation. Now with these properties, believe it or not, we are more than halfway into Gaussian processes. You're just going to apply them and derive Gaussian processes. Of these properties, the one that looks the scariest is probably the conditioning property, and you can make it, I guess, you can approach it or make it less scary by seeing the analogy to the two variable case, and just believe that that monstrous expression is just a multivariate generalization of that. Yeah, question.
Just out of curiosity, how do you go about proving something like that? The property 3.
Property 3, how do you go about proving that? I would say that's beyond the scope of this course. Just take it for granted, and you can. So there is a book called, if you're interested, it's called Gaussian Processes for Machine Learning, and I would point you to that. There's also some notes that I have linked to in the syllabus page, and it has an appendix where there's a proof for that. So. All right, so Gaussian processes. So in Gaussian processes, what we want to do is, so let me try to draw an analogy with multivariate Gaussian and Gaussian process. Right? In case of the multivariate Gaussian, we had say y1, y2, yd according to some normal with mean mu1, mu2, mu d and some covariance. Okay. Now in Gaussian processes, what we instead have is a function f distributed according to what we call as a GP over a mean function m and a kernel k. Right? So this is a direct analogy between multivariate Gaussians and Gaussian processes. In multivariate Gaussian, we had a vector which had a corresponding mean vector and a covariance matrix. In a Gaussian process, we have functions distributed according to a mean function and some kernel. Right? So there is a direct one-to-one mapping between positive definite matrices and kernel functions. Right? And here we are now going to use the properties 1, 2, 3, 4 to derive Gaussian processes for machine learning or Gaussian process regression in a pretty straightforward way. Right? Now, as you might remember, in vectors, we index them with some index, and the corresponding thing to do with functions is to evaluate a function at some input. Right? So you can think of this as a vector, which is basically a set of all evaluated. So f of x1, f of x2, basically every possible input for that function will have a position. That's the mental picture to have. That's not the right definition, but it's a very good mental picture to have. And the value evaluated by the function is the value of this infinitely long vector at that position. Right? So where you had indices, you have inputs. Right? And now we are going to use the conditioning property and the marginalization property of Gaussian vectors and limit ourselves to just those elements that exist in our training set and to the test example that we want to make a prediction on. Right? So this means if we marginalize out all irrelevant examples, so basically examples not in training and not in test, right? Then we basically get something that looks like this. F of x1, f of xn, and then let's call f of x star 1 until f of x star n star, right? The set of all examples in our training set and the set of all examples in our test set. And we are going to assume that the Gaussian process has a mean 0. So most of the times we assume the mean function to be just a 0 function, right, times the kernel function evaluated, right, the kernel function evaluated on the set of these examples. So this gives us the kernel matrix, just like how we saw in the case of the Mercer's theorem, that you take a kernel function and evaluate it on a set of points to construct a kernel matrix, then that kernel matrix is positive definite. Similarly, here we evaluate k of, in this case, x1, x1, and so on, k of x star 1 or n star. Let me write this more clearly. K of right. And Mercer's theorem tells us that this will be positive semi-definite. And so this is a valid multivariate Gaussian distribution. Yes, question?
Does Mercer's theorem also tell us that each element of the kernel matrix also has to be greater than or equal to 0?
No, it need not. So should each of these be non-zero? No, they need not be non-zero. They can be positive.
Or greater than or equal to 0?
No, they can be negative. Some elements can be negative. If you have.
Didn't it say that every submatrix also has to be positive semi-definite?
Yes, every submatrix has to be positive definite. So what's the meaning of submatrix? That's a good question. So if you have a matrix, let's say it has n rows and n columns. Now choose a few index values, let's say 2 and 7, right? And extract out rows 2 and 7 intersected with column 2 and 7. These 4 make your submatrix. So in order to reduce it to a submatrix of size 1, that can only be the diagonal values, right? So row 2 and column 7 will not give you a submatrix. So row 2 and column 2, that element is a submatrix.
Oh, okay. So but then everything along the diagonal has to be greater than.
Yeah. So k of if you evaluate k on the same element in 2 places, that will always be non-negative. So submatrix doesn't mean any arbitrary block.
So that's what
Yeah. So submatrix means a matrix that you get by choosing the same set of indices for rows and columns. Good question. Thank you. All right. Now we will represent this in a more compact way, where I will write f to be the examples as the training set and f star as the function evaluation at the test set, equal to normal of 0, and I will call this block to be k of x, this block to be k of x star. I guess we've been writing star as a prefix, as a subscript. Then again k of x star and x, and k of x star. Again, so this is the same thing that's written above, where we are looking at just those examples that are of our immediate concern. So examples in the training set and examples in the test set. And this is like you're marginalizing out all the other infinitely many examples that are not of immediate concern. Yes, question?
When we think about functional spaces, will kernels always act as like the similarity matrix, or is it just for the Gaussian processes?
So so the question is, do kernels act as some kind of a similarity metric in general, or is it only in the case of Gaussian processes? The answer is kernels always act as some kind of a similarity metric, and you can use any kernel and come up with a covariance matrix for a Gaussian process. There's no limitation of which kernels you can or cannot use, as long as it's a valid kernel that can serve as a covariance function for a covariance matrix or for a Gaussian process.
Is the reason because of the definition that we get like dot product of x and z equals to 0 to
Exactly. The reason is because a kernel can be interpreted as a dot product in some higher dimensional feature space, and dot products are a good similarity metric, so to speak. Yeah. All right. Was there another question? Right. So we started with an infinite dimensional functional space, and then marginalized out every example that is not of immediate concern to reduce ourselves to a Gaussian distribution, a multivariate Gaussian distribution over the set of training and test examples. All right. And with that, we're almost there. Once we are in vector land from process land, all our properties that we just reviewed can now be directly applied. So these properties that we covered, conditioning, conditioning especially, this is, you need to be able to invert a matrix, right? So this is we are dealing with finite dimensions here. Right? So we got the f vector to be this, and in general our y vector are y we saw was f of x plus noise, where it so happened conveniently that the noise was also Gaussian followed a Gaussian distribution, and we're going to use the summation property to add these two, right? So we get y star equals f star plus epsilon stars, and this is now distributed as a normal distribution where the means of f's were 0, the means of our errors were 0, so we are still at 0 here, but the covariance matrix is now k of x plus sigma square I, k of x star, k of x star, and k of x star plus sigma square I. Right? Any questions in this? So f followed this distribution by marginalizing out all the examples that were not of immediate concern, and by our noise hypothesis that we have Gaussian noise in our observation, we get a distribution over the y's to be f's plus the noise, and over here we are just using the summation property and adding up the covariances. Epsilon, the entire epsilon vector follows normal 0 and sigma square I. right? So you just add it here, it only adds along the diagonal. And this is the matrix that we're going to now work with. Right? And given this matrix, we are just one step away from finishing up Gaussian processes. So the probability of y star given y and x star and x and x star is kind of implicit in the indices that we have chosen, is now, or another way to put it is y star given y x star is distributed according to a normal distribution with some mean mu, call it mu star, and some covariance sigma star, where this mu and sigma star are calculated according to this conditioning rule. We apply the conditioning rule to this mean and this covariance, and we get mu star equals k of x star comma x times k of x plus sigma square I inverse y, and sigma star equals k of x star plus sigma square I minus k of x star x times x plus sigma square inverse k of x star. This is a complex looking expression, but this is exactly the same as this, where we plug in kxx in place of sigma AA, k x star in place of sigma bb, and k of k of xx plus sigma I square in place of sigma AA, and so on. Right? We're just applying the conditioning rule, and we got our posterior predictive distribution. Right? This is the posterior predictive distribution of Gaussian processes. Yes, question?
Can K be thought of as some kind of a covariance? Like that one?
Yeah, so over here, this is just a shorthand notation for the kernel matrix you get for evaluating on that set of examples. So K is, so there is a one-to-one relation between kernels and covariances, right? Covariance functions and kernel functions, there's a one-to-one relationship. Any kernel function can be used as a covariance function. And that's probably the most important takeaway from this class, for in general, that kernel functions and covariance functions are essentially the same. Right? So this is the posterior predictive distribution for Gaussian processes, and the expression looks pretty complex, but everything here is straightforward linear algebra. Right? We have the set of x's, we have the set of x stars, and just compute this, and you get your posterior predictive distribution for the test examples. Nowhere here do we have y star. That's important because we are making predictions about y star. We only have y's, x's, and x stars. And given this, in order to kind of construct a good GP model, the most important decision step, or rather the only decision step, is to come up with the right kernel function or to come up with the right covariance matrix. Right? Once you come up with the right covariance matrix, everything else is pretty much set in stone. Right? right? Everything else just flows along once you choose what your kernel matrix is. There is no loss function, there is no gradient descent, there is no fitting of models. All that we do is, given the set of x's and y's in our training set, we just remember them, choose a kernel function, and then wait for test examples. Once we get our first test example, we plug it into this expression and obtain a predictive distribution. Right? And because we covered this in SVMs as well, and because this is a kernel-based method, a consequence of that is that we need to remember our training set all the way into test time. Right? And that is basically showing up here, because you need to have the x's and y's from your training set in order to make the prediction. Yes, question?
This is the kind of result that we get, it's very similar to that of like a generative model, right?
So the result what we get here is similar to a generative model. Can you expand on that a little bit?
So like y given x.
Yeah.
Or in this case y star given everything, and x is also Gaussian given like based on the assumptions that we made initially.
Yeah, the fact that the posterior ended up being a Gaussian is actually a property of Gaussians, right? We saw that when you start with a distribution that is Gaussian and you condition on a few variables, what you end up with is also Gaussian. So that's a property that is kind of unique to Gaussians, where you start with a multivariate Gaussian, you marginalize out a few of them, you still end up with a Gaussian with a smaller dimensional space. You start with a Gaussian vector, you condition on a few of them, you still get a Gaussian with what's remaining, right? And that's why the posterior also is now Gaussian, because we conditioned on the y's that we observed in the training set.
And why is this called non-parametric exactly?
The reason why this is called non-parametric is because we did not come up with any kind of a functional form for our prediction function.
Isn't that a functional form? Mu star and sigma star?
So mu star and sigma star are, well, you can think of them as a functional form, but what you will realize is that there was no fundamental limit on what these values could have been. So next I'm going to show some visualization that will probably give you a better hint of why this is called non-parametric. Maybe that might answer the question. Let's move on to some visualization. Any other questions on this? Yes, question.
Can we do the same things for other exponential families?
Can we do the same thing for other exponential families? Great question. So Gaussian processes is what's also it's a type of a stochastic process. And if you're familiar with stochastic processes, you can think of them as a collection of random variables with some kind of an index set. And this is a Gaussian process is essentially a collection of random variables where the index set is the domain of your function, right? And in theory, you could do the same, go through the same exercise for any other distribution other than Gaussians, but the other distributions may not have. First of all, they may not have multivariate versions. So, for example, a Poisson distribution, there is no multivariate Poisson. I mean, you can have a collection of Poisson, but there's no multivariate version of it. You can still have, for example, you still do have a Poisson process, but they don't have the nice properties that if you condition on something, what remains also is a Poisson process, right? But that's true only for Gaussian processes. Where if you condition on something, what remains is still Gaussian. If you marginalize out something, what remains is still Gaussian.
But if we knew that our data was actually made through some process in exponential family, then this would be a nice idea to go and target that exponential family, right?
So I guess the question is, now what if your data is distributed according to some exponential family, right? And over there, the most common approach that you see is the f over here, instead of f being y directly, so we assumed y is equal to f plus epsilon. right? The most common thing to do is there's going to be some kind of you can call it an activation function or the G function that we used in GLMs, and you can have the natural parameter be distributed according to Gaussian. You can do something like this, right? And your observations Y will now go through this nonlinear transformation to make the actual observations. But once you do this, you lose the conditioning ability, right? In Gaussian processes, because the noise was additive and the noise was also Gaussian, we got the Y's in a Gaussian form again, right? But if this is nonlinear, if it's not a simple summation of two Gaussians, your Y's will no longer be normally distributed, and you cannot do the conditioning and so on. So yeah, you can do it in principle, but you don't get these simple expressions. This question.
Going on that question, is there a more generalized conditioning rule for other elements in HMHM? Is there any way to generalize properties?
So the question is, do these properties, do they hold for other exponential families? Yeah, so these properties are very unique to Gaussian, which is what makes Gaussian processes kind of nice to work with, right? And you may have actually also come across, especially if you have some kind of a background in finance, you may have come across like Brownian motion and Wiener processes. And basically the way to connect that with what we saw today is a Wiener process or Brownian motion is a GP, is a Gaussian process with K of say S comma T equal to just min of S comma T. For this particular choice of a kernel, you get the Wiener process. If you don't know what a Wiener process is, you don't have to worry. But if you're, if you have some background in finance and you know what's Brownian motion and Wiener processes, it relates to what we saw today by this particular choice of kernel function. Right, let's do some visualization. Where's my browser? There you go. All right. So this is I see another cursor. I don't know. All right. So this is a web page that I've kind of preloaded. It is from a website called distill.pub. I would highly encourage you to visit this website. There are great articles explaining things about machine learning, and I'm a big fan of it, and you probably too should be one. Anyway, so this is, they have some really cool visualization of Gaussian processes, and I'm going to scroll all the way down to the very last visualization, which is pretty cool. Oops. Yeah, over here, right? So this is some kind of a functional space, an abstract functional space. So the x-axis over here is our space of inputs. It need not necessarily be, just scalar real value. Think of it as some abstract space. And now, the moment we choose a kernel, so there are three choices of kernels here: an RBF kernel, which is also called the Gaussian kernel, a periodic kernel, and a linear kernel. So once we choose an RBF kernel, this defines a prior on our functional space, right? And these curves that we see here are samples of functions drawn from this Gaussian process prior, right? And once we have this, we can now observe our training data and start conditioning on them. So if you click over here, this means we have now conditioned on this particular input in our training of having this particular y value. And similarly, as you keep conditioning on things that we observe, right, the posterior distribution of our GP, of our Gaussian process, takes this form. What this essentially means is, for any test example that might have an x value over here, the GP, if we marginalize out everything else except that single slice, right, that's going to be our posterior predictive distribution for the new x star, right? And this basically tells, for examples, for test examples in this region, our posterior predictive distribution has a very small variance. Means we are very confident of what those values should be. Whereas over here, in regions where we haven't seen much of training data, the prediction value will be pretty broad. In the sense, we'll have very high variance. We are less confident about making predictions in this region where there weren't much training examples nearby, as opposed to here where the posterior distributions have very small variance, which means we are making very tight or confident predictions. This question?
So when you marginalize, you said you'll be taking a vertical slice of it, and then, okay. Does this look like overfitting to you?
So back to the question, does this look like overfitting, right? So this is like a fundamental trade-off between parametric and non-parametric models, right? Non-parametric models are extremely flexible in the sense if your data follows some pattern, your function, your posterior distribution in GPs will follow that pattern, right? And there is a common criticism that non-parametric models can overfit pretty easily. But in cases where you have a reasonable amount of data, non-parametric models tend to work pretty well. This might look like overfitting, and I guess that's, as they say, it lies in the eye of the beholder. You might call this overfitting, but overfitting is a loose concept in general. It's hard to kind of give a formal definition of what overfitting means. And you could call it overfitting, but for example, if you use a different kernel, it would look like this. Now you uncondition, you get. Now this is the prior, and these are samples from, the gray lines are samples from that GP prior. And as we start observing training data, we're basically just conditioning. And these are the pink band is basically represents some, I guess, 95% range of the posterior distribution. And without conditioning, it's like the 95% range of the prior distribution. Right? Or you could use a combination of the two, compose the two kernels, and get something like this.
What does that mean, like compose kernels?
Yeah, so you can construct kernels by taking existing kernels and kind of composing them. You'll see some of that in your homework 2. You'll probably do some kernel composition. As long any function that obeys the properties of a kernel is a kernel, and you can take existing kernels and compose them with certain rules and still get valid kernels. Right. So this is I think a pretty intuitive and a nice visualization of Gaussian processes where you start with a prior. The choice of the kernel gives you different priors, right? Just the choice of the kernel without observing any data, right? You choose different kernels, you get different priors. The choice of the kernel gives you a different GP prior. And depending on the choice of the kernel that you've chosen, observing data gives you different kinds of posterior, GP posteriors. Right? This is a GP posterior if you use a different kernel. Right? And at test time, to repeat, your test example will lie on the horizontal axis at some point, and your predictive distribution is going to be the vertical slice or marginalize out everything else, and that's going to be like the Gaussian distribution, whose mean follows the red thick line, and the border lines kind of define the 95% range of that Gaussian distribution. Yes, question.
So when you are given this data and you are asked to implement this like an algorithm on this, how will you choose when to go with the Gaussian process? Because this looks like a good fit for a straight line, like linear regression.
Yeah, so the question I guess is when do you use a Gaussian process, right? And the answer is going to be pretty boring, as for almost all answers in machine learning. See what works well on a cross-validation set. Right? It sounds and that is probably the most pragmatic answer, and that should be the answer you should always go with. Always see any change that you do, how well does the performance, what kind of performance you get on a cross-validation set. Yes, there was another question.
What is that heat map on the right?
Yeah, so the heat map on the right is showing This is like the kernel matrix. The kernel matrix that you get by conditioning on or the covariance matrix that you get. So in the posterior predictive distribution, we ended up with a mean and a covariance. So this is like, I think this is the posterior covariance. This question.
Should the choice of kernel also be what works best in cross validation, or is there a way of?
Yeah, so the question is, should the choice of kernel also be something that works well on cross validation? And the answer is yes. And there are also techniques with which you can learn a kernel. We didn't cover it today, but the book that I refer to, the Gaussian process for machine learning, it gives you a good overview of how you can even learn kernels from data, right? Not just handcraft them. Yes, question?
Can like two kernels, composition of kernels can be looked as composition of functions with two inputs?
So can composition of kernels be interpreted as composition of two functions with two inputs? In general, no. I wouldn't think of it that way. It's just that you get a different kernel. All right, that's about it for today.